Finding zeros of polynomials, Descartes' rule of signs. This video will help you use the rational zero theorem to identify possible roots of a polynomial function, identify the number of roots in a polynomial function, use Descartes' rule of signs to narrow down the number of roots that would need to be checked, and use the linear factorization theorem to write a polynomial function given the roots. Alright, so we are going to take a lot of ideas, put them together to find the zeros of a polynomial. And remember, the zeros of a polynomial, now we're getting into more complicated functions here. And so, you know, our polynomials could cross the x-axis at several locations. Here, and those locations, remember, are the zeros or the roots. So every time we cross here, we call that a zero or a root as we cross over the axis, the x-axis. And so the first thing we're going to use here to help us narrow this down is what's called the rational zero theorem. And what that does is it gives us a bunch of different choices or possible choices as zeros. So once we get that list of choices, then we want to kind of figure out from that list of choices and kind of narrow it down and actually find the roots. And so a couple other ideas will help us do that. One is that the degree of the polynomial, and again, the degree is the highest powered term in the polynomial. So the degree will tell us how many roots there are. So if we have a polynomial, an nth degree polynomial, meaning it's to that power, our highest power term is to the nth degree, then we get exactly n roots. So that helps us know how many roots it is that we're trying to find. Okay, another idea here is that if we have imaginary roots, meaning we have an imaginary number in the root, or an irrational root, and an irrational number is a number that cannot be represented as a fraction, a non-terminating, non-repeating decimal number. Good example of an irrational number is like pi. So if we have crazy numbers like that, or imaginary numbers, they're always going to appear in a conjugate pair. And the last one here is Descartes' rule of signs. And Descartes is the same Descartes you would study in your philosophy class. He was also a mathematician, and he came up with a rule of signs that will help us narrow down this list that we make from step one, which is the rational zero theorem. So Descartes has found a way to narrow that list down. So now that we've talked about all of those four ideas that are going to help us to find these roots or zeros of our polynomial function, let's look at each one individually to understand what we're going to use them or how we're going to use them. So let's start with the rational zero theorem here. The rational zero theorem helps us to narrow down the number of possible rational roots. Now remember, rational, that means numbers that can be written as a fraction. The rational roots of a polynomial using the ratio of the factors of the constant term and the factors of the leading coefficient. So notice if we have our polynomial here, polynomial function here, our constant term or factors of our constant term are going to be factors of our very last term in the polynomial. We're going to write these polynomials in descending order. So we'll take factors of the constant term over factors of the leading coefficient. Now the leading coefficient is the coefficient on our highest power term. So we're going to take factors of this guy divided by factors of that guy. And those combinations are going to be our possible rational roots of our polynomial function. Now, when we do this, you know, factors of this constant term divided by factors of the leading coefficient, there is a lot of choices there. And so what other people have done now over time is they've worked to kind of narrow that list down. So now let's go ahead on to the next idea, and these next kind of ideas help us narrow that list down. The first one that helps us narrow it down is we will know how many roots we're looking for, because all we have to do is look at the highest power on our leading term, and whatever power that is, that's how many roots we had. For example, if our leading term is a fifth power polynomial, then we're going to have 5 roots. Fourth power polynomial, 4 roots, and so on. Okay? If we have one imaginary or irrational root, we always get a second one. So the reason these always occur in conjugate pairs, because if we're going to come up with an imaginary root or an irrational root, we're always going to be using the quadratic formula to do so. And when we use the quadratic formula, we have this plus and minus sign. So that's why we're always going to get a pair of these. Whenever one occurs, there's always going to be a second one. Okay. And here's our last idea that helps us narrow down the number of choices, or number of things we have to check. And this is Descartes' rule of signs. So we've got our polynomial function here. Okay. The number of positive real roots is either equal to the number of sign changes, and sign changes, all we're talking about here is going from one term to the next. If we change from a positive to a negative or a negative to a positive, that's a sign change. So the number of positive real roots is either equal to the number of sign changes in our whole polynomial function, or less than the number of sign changes by an even integer. So for example, if we looked at ours here and we had 5 sign changes, 5 would be one possible case for the number of positive real roots, and then it's going to drop by increments of 2. So 5 would be one possible, then 3 or 1. Those would be the number of positive real roots we could potentially have in this polynomial based on its sign changes. The negative real roots, the same idea. Instead of just looking at the polynomial function as f of x, what we do is we put a negative x into the polynomial. So we'd put a negative x in all of these terms, kind of simplify it down. Once we got it simplified down, we would look again at the sign changes, and the sign change rule for negative is the same as positive. So it's the number of sign changes that we have, or that number decreased by 2. Same as this, 5, 3, 1. That could be a potential negative real zeros of the polynomial function if we had an overall sign change of 5. Okay, so these are the ideas, and they might not be totally clear right now, but when we look at an example, it'll kind of start to come together here. First thing we want to do here is just figure out how many roots we're going to have in total. And all we have to do that is take a look at our first term, highest power term, and you'll notice this is a polynomial of degree 3, so we're going to have 3 roots. Now, not all of those roots are going to be real. Some of them could be imaginary. All right? All right. Now, the next thing we want to do is use the rational zeros theorem to figure out our possible rational roots. Now, this is not all of our roots, but these are the ones that are real numbers that can be written as a fraction. All right? So what we do is we take factors of the last term and we divide that by factors of the coefficient of the first term. So let's see. Let's look at factors of 5 or negative 5. Either way, it won't make a difference. So factors of 5, we've got plus or minus 5. We could take 5 times 1, or we could take negative 5 times negative 1. So plus or minus 5. And we've also got plus or minus 1. Those are all the factors I have of 5. And this one's going to be easy because you notice if I look at my leading term here, my coefficient there is 1. So for 1, my factors are really just plus or minus 1. And so I want to take these and write them in fraction form. The last term, factors of my last term divided by factors of my first term. Well, this is going to be pretty easy. Really, I have this. I have plus or minus 5 up top, plus or minus 1 up top, and then plus or minus 1 down below. So that will give us, as a list of factors here, we could have plus or minus 5 and plus or minus 1 when I do that division. Notice these terms up here are getting just divided by positive or negative 1, so we just end up with those as our possible list of roots. Okay, so right now we would have 4 possible roots to check. So we would want to put these guys back into our function basically and see if they gave us a 0. Now, one way to quickly do that is instead of just putting these guys back into our function here, let me erase some of this stuff, putting these guys back into our function here, we can use synthetic to division to find out if they are a root. That'll actually save us some time here too. So one way to do it is take these guys, plug them in. A faster way to do that is to use synthetic division and see if they divide in evenly, because if they divide in evenly, then they will be a root or a factor. All right. Before we do that, though, let's use Descartes' rule of sign and see if we're going to have positive roots here or negative roots. It will tell us how many we're going to have of each, or potentially how many we'll have of each. So let's see. So the first thing we do for the positive roots is we just look at our function here and we count the sign changes. So I'm going across here. I'm starting with a positive, going to a negative, so that's a sign change of 1. And then negative to positive, so that's 2. So that's 3. So we have 3 potential positives. If potentially we end up with a situation where we have either irrational or imaginary roots in this 3 possible, then it would drop these down by an increment of 2, because remember, irrational and imaginary roots always appear in a pair. So we could have 3 positives or 1 positive rational root. Okay, depending if we ended up with an imaginary or an irrational in there. All right, let's look now at negative roots. So all we're going to do now is take our original polynomial function and plug negative x in there. So I'd have this negative x cubed minus 4 times negative x squared plus 8 times negative x minus 5. So let's see. So if I cube negative x, that will give me negative x cubed. This is going to stay, negative x squared is just going to be x squared, so this will stay negative 4x squared. Here, this is going to be a negative 8x, and here a negative 5. So let's look at the sign changes now. Well, we don't have any sign changes. They're all negative. That tells us there are 0 negative rational roots. So Descartes just saved us a bunch of time, because originally for the roots that I had to check up here, I was going to check plus or minus 5, plus or minus 1. Well, Descartes' rule of signs now has ruled out any negative roots. So when I'm going to check these things, I'm only going to check the positives here, positive 5 and positive 1 for my rational roots. All right, let's kind of look here and put this together. I kind of talked about this, but let's formalize this. After Descartes' rule of signs, we could have 3 positives, 0 negative roots, and 0 imaginary roots. Because remember, we have 3 roots in total, and if they all end up being positive rational, we could have 3 positive rational and none of the others. All right? We also could have this, 1 positive here, and 2 imaginary. That's another way we could come up with 3 roots here. 1 positive, 2 imaginary, because remember, if the imaginary ones show up, they're going to show up in a pair. Descartes' rule of sign tells us we don't have any negative roots, so that's not going to be a possible combination we could have. So those are all the possible combinations of how these roots could work out. Now that we've narrowed this all down, and we know what roots to check, we're going to use synthetic division to check these things. And again, remember, since we don't have any negatives, we're only going to check positive 5 and positive 1, and 1 as potential roots here. So let's start with 5. So we're using synthetic division here. If 5 divides in this evenly, then it will be a root. So I'm going to take my coefficients here. So I'm taking my coefficients off of these numbers here. So 1, negative 4, positive 8, negative 5. Okay, so the first thing I would do is bring down the 1. Then I multiply 5 times 1, which is 5. I write that up here. Now I'm adding as I go down the column. So that would give me a positive 1 again. Then I'd multiply 5 times the 1 to give me positive 5. Adding down the columns again, 8 plus 5 will give us 13. So 13, and then 5 times 13 would give us 50 plus 15, 65. Well, you can see this is not going to be a root. Negative 5 plus 65 gives us a remainder of 60. So that tells me that 5 is not a root. All right, let's try 1. Bring down the 1, multiply. 1 times 1 is 1. Adding down the column, negative 4 plus 1 is negative 3. 1 times negative 3 It's negative 3. Adding down the column, 8 plus negative 3 is 5. 1 times 5 is 5. And now when we add, you can see here in our remainder spot, we get 0. So that tells me that 1 is a factor here. All right, and kind of let's see where we stand right now. If 1 is a root or a 0, so if 1 is a root or a 0, then that tells me that x minus 1 was the factor there. Okay, since positive 1 was the root, it tells me that x minus 1 was a factor. And let's see what we have left over here. So this would be my remainder. That would be my constant term. This would be my first x term. And this would be my x squared term. Okay, so that's where I stand right now. I've found one of the roots. I need to either factor this or use the quadratic formula to find the next roots. So let's try to factor it real quick, since that's always easier. X and x. Last term is positive, middle is negative. That means I have to go minus minus. But let's see, factors of 5, 5 and 1, that would not give me 3. Really, this is not going to work, so that's not going to factor at all. So I got to use the quadratic formula here. Okay, let's give ourselves some room here to work this out. So we're going to have negative b, which would be positive 3, plus or minus square root of b squared, negative 3 squared, minus 4 times a, which is 1, times c, all over 2a. Well, a is 1, so that's just over 2. Let's simplify this guy down. So this is going to give us 9 here, and this is going to give us 20, all over 2. Let's see, so 9 minus 20 is going to give us negative 11, all over 2. And you can see here that we're going to end up, now with an imaginary number, since we're trying to take the square root. Since we're trying to take the square root of this negative 11. So let's write this. 3 plus or minus I. Let's pull an I out of there. So let's say I times the square root of 11 over 2. You can write it that way, but it's easier to see our factors then. Let's list our factors out, and I'll write them as separate factors when we do that. So we knew our zeros were, we had a 0 of positive 1. We have a 0 of 3 plus I times the square root of 11 over 2, and 3 minus I times the square root of 11 over 2. So there are the zeros now of our polynomial function. Let's go back up real quick and check. You know, we listed our possible combinations here and see which one we have. Notice we have one rational root. I could write 1 as a fraction. It'd be 1 over 1. That would make it a rational number. And it looks like 2 imaginary roots. And if we go back up here and look at our combination, it was this combination right here that we ended up having. 1 positive rational root, and then 2 imaginary roots. Okay, so now it's time to give this a shot. You know, if it's not totally clear, you might want to scroll back in the video that I just showed you before. You might not need to see all the details, but you could scroll back through and kind of watch my process, or at least the beginning of my process, to get some hints on how to do this. But it's important that you give this a shot, even if it doesn't work out perfectly. Give it a try, and then that's how you learn. All right, so pause your video player and answer this question. When you're done, hit play to see how you did. All right, let's start. Question 1 here, I think, is the easiest one. How many roots do we have? Well, the polynomial is written in descending order, so all I got to do is look at the highest power term. Looks like a 3 is the maximum exponent we have here on our polynomial function, so we can have 3 roots to this guy. Possible rational roots. Well, we need to take factors of negative 4 divided by factors of positive 2. So what that kind of looks like is this. In the numerator, factors of negative 4, well, plus or minus 4, plus or minus 1, combinations of that multiplied together would give us a negative 4. And then we could also do plus or minus 2. Well, 2 gets multiplied by 2 to make 4, so that's all the possibilities we have there. Now in the denominator, to make 2 combinations there, I could take plus or minus 2 times plus or minus 1. Now we need to list all these guys out as fractions. So let's see. So one thing I could do, let's start with the highest or the largest term up here, was 4 over 1. So that's going to be either positive 4 or negative 4. So that's one possible. Plus or minus 4 is one possible there. All right. If I look at the 4 divided by 2, that's 2. So I could have plus or minus 2 as a possibility there. All right, that kind of does it for 4. 4 divided by 1, and then 4 divided by 2. Let's go to 1. So 1 divided by 1 would give us plus or minus 1 to check. And then 1 divided by 2 would give us plus or minus 1/2 to check. All right. That does it for 1. Now let's look at 2. I could do 2 divided by 2, which would give us plus or minus 1. Well, I've already got that listed right there, so I don't need to repeat it again. And if we did 2 divided by 1, that could be plus or minus 2, but I already have that listed here. So here are all the options here, or all the possible rational roots I would need to check using synthetic division. Now, we want to narrow that down, so let's use Descartes' rule of signs here to narrow that down. So we're using Descartes' rule of signs here. Let's start for positive roots. We would say, all right, let's look at the sign changes. Just one sign change. So there is up to one positive root here. Okay? Let's look at negative. So we want to do f of negative x here. So 2 times negative x cubed minus negative x squared minus 9 times negative x minus 4. All right, let's simplify this. This is going to stay negative, negative x cubed. So this would be negative 2x cubed. That will stay positive. Negative x squared be positive x squared, but then the minus sign out front, so that would be minus x squared. Negative times negative is positive, so plus 9x. And then finally, minus 4. So let's look at the sign changes now for negatives. Not a change there, but 2 changes. So 2 negative rational roots. So it wasn't as nice as the last time where we totally dropped out all the negative ones. We do have a combination here of positive and negative. So let's look at our possible combinations here, okay? One thing that could happen is we could have 1 positive root, 2 negative roots, and 0 imaginary. That would add up to a total of 3 roots. Remember, we have 3 roots in total, and this is a possibility. 1 positive, 2 negative. That could happen. These 2 negative roots could end up being imaginary. You know, these don't have to be negative roots. It's just a possibility. So we could have this 1 positive, 0 negative, 2 imaginary. So I think that's really all the possibilities we have here. You know, we can't take this 1 positive root away, because if we take this positive root away, we can't add it down here, because it'd have to come up in a pair. If it's going to end up in imaginary, we're going to have to end up with a pair. So there's no way to take anything away from that. So when I'm looking this to decide where to start with my synthetic division and what to try, you know, I could have negative roots here. I could have up to 2, but I could also have 0 of these things. So I want to go ahead. I don't think it really helps to decide whether the positives or the negatives work. We're just going to go ahead and try one out here, because we could have a possibility of both. Let's try a positive 1/2 here. Okay, so I'm taking the coefficients off of this guy up here. So 2, negative 1, negative 9, negative 4. So bring down the 2. 1/2 times 2 gives us 1. Add those together, that gives us 0. 1/2 times 0 is 0. Negative 9. 1/2 times negative 9 would give us negative 4.5. So that's not going to work. So positive 1/2 was not it. Let's try negative 1/2. All right, so now the Let's try negative 1/2. So I would bring down the 2. Negative 1/2 times positive 2 would give me negative 1. Negative 1 plus negative 1 would give me negative 2. Negative 1/2 times negative 2 would give me a positive 1. And then negative 9 plus positive 1 would give me negative 8. Negative 1/2 times negative 8 would give me a positive 4. And there it is. There's our factor. We get a remainder of 0. Scroll down here and give us a little bit more room. So now we know this. We know if negative 1/2 was a root, then we know that x plus 1/2 was a factor, and 0 remainder. So this is going to be our constant, our x term, and our x squared term. So 2x squared minus 2x minus 8. Okay, so we would look to factor this guy. Notice this 2 is a common factor in all of those things, so I'm going to pull that 2 out front. Oops, yep, minus x minus 4. All right, so we would try to factor this. X and x, and our last term is negative. Our last term is negative here, so plus and minus. 4 and 1, 2 and 2. Neither of those are going to work to give us a negative 1 in the middle, so we are back to the quadratic equation here. All right, so it looks like we're going to get 1 plus or minus the square root. This is going to be positive 16. You can see the negative 4 times the negative 4. So 1 plus 16 is going to give us positive 17 over 2. So this is not imaginary. Notice we're taking the square root of a positive number here, but this is going to be an irrational root. All right, so let's see. So we've got yeah, we can just leave it like this, really. So our list of roots is going to be negative 1/2. So our zeros, or you can call them roots, either way. Zeros or roots means the same thing. Is going to be negative 1/2, and then we're going to have 1 plus the square root of 17 over 2, and 1 minus the square root of 17 over 2. For our zeros there. Now let's look back and see which combination that was. So it's right here was the combination that we ended up having. Notice we had one positive root, which is right here, and then we had 2 negative roots. This is a negative number, and here if I subtract the square root of 17 from 1, it will end up being negative as well. Okay, so up until this point, what we've been doing is, given a polynomial function, find the zeros or find the roots. Now we're going to talk about the linear factorization theorem. And the linear factorization theorem kind of goes a different direction, the other direction. The linear factorization theorem enables us to find a polynomial function given the zeros. So now we're going to start with the zeros and turn around and come back and find the polynomial function. And here's how this works. The linear factorization theorem, a polynomial of degree n will have n roots. We already knew that. So an nth degree polynomial can be expressed as a product of a non-zero constant. So we're going to take the product, meaning we're going to multiply a non-zero constant with however many linear factors we have. You know, if we're talking about a 4th degree polynomial, we'll have 4 factors then. Each of these factors is going to have the leading coefficient on each of these factors will have a coefficient of 1. So if we started with a polynomial like this, we can express it as something that looks like this. Here's our non-zero constant out front, and we're going to multiply that times however many factors we have, whatever degree that we have here, and we're always going to get a 1 as our coefficient on each of these factors, and we can express that then as a product of these factors. Now sometimes these numbers here will be real numbers, and sometimes these will be imaginary numbers. And I guess that's what we say right here, where some of these factors may be complex numbers. And if we do have a complex number, it's always going to appear in a conjugate pair. So for example, if we have one factor of I, we'll have another factor of negative I there. Okay, well, let's start with the roots. We've got a 4th degree polynomial function. And if we look at the roots over here, we only have 3 roots. So something's not right. If we're going to have a 4th degree polynomial, we need 4 roots. And here it is where it is, right here. It's with this I. So remember, if an imaginary root appears, it has to appear in a pair. So if we're going to get positive I, we are also going to get negative I as a root. Because remember, imaginary roots will always appear in a pair. So now we have 4 roots. Now we're ready to use a linear factorization theorem to set this up. So let's see. This is what we want right here. We want to set up kind of a generic form of that. So we know that my function f of x is going to equal to some constant out front, and you can call that a sub n if you want to, or any other constant out front, a sub n, and it's going to be times now these 4 factors, which are based on our 4 roots or zeros up here. So if negative 2 was a 0 or a root, then x plus 2 would be a factor. If positive 2 is a 0, then x minus 2 would be a factor. If I is a root, then we would have x minus I as a factor. And if negative I was a root, we'd have x plus I as a factor. All right. What we want to do next now is we want to simplify all of this stuff down. So I'm going to start by multiplying those 2 together and multiplying those 2 together. And I think this thing will simplify for us. X plus 2 times x minus 2 is going to give us x squared minus 4. Remember, that middle term drops out. And here with I, we'll get the same thing. Since we got plus I and minus I, that middle term is going to drop out. So I'm going to get x squared minus I squared on the end. Well, remember, I is the square root of negative 1. So if I squared that, if I take the square root of negative 1 and square it, that is just going to give me negative 1. So that allows us to simplify this even more. X squared minus 4 times minus a negative 1 is just going to be x squared plus 1. All right? That's the most I can simplify it now, and I've almost got this polynomial function here. I don't need to multiply these 2 factors out here. I can leave them just like that. The only thing that's missing is I need to find what this constant term is out front, and that's where we use this information right here. If I plug 3 into this equation, I should get that f of x is equal to negative 150 over here on the right. So let's go ahead and do that. If I plug a 3 in for x, it should be equal to negative 150. So negative 150 a sub n, and that's when I plug a negative 3 in here and a negative 3 in there. So let's see, negative 150, give myself some room over here, a sub n, let's see, if I square negative 3, that's going to be positive 9. Here again, square negative 3, that's going to be positive 9. Let's come up over here to finish. So negative 150 equals a sub n times 9 minus 4 is 5. And then 9 plus 1 is 10. So it looks like negative 150 equals a sub n times 50. A sub n, it looks like negative 3. So now that I found a sub n, I want to write my whole polynomial function here. So f of x is equal to negative 3 times x squared minus 4 times x squared minus I squared. Or actually just plus 1. It's cleaner to say plus 1 here, so let's just say that. Plus 1. And there is my polynomial function. Okay, let's go ahead and practice this idea. Pause your video player now, and we're finding a 3rd degree polynomial function with real coefficients such that negative 3 and I are zeros of the function. And just like that last question, I'm going to have to add a little bit of information here. That f evaluated at 1 is going to give us 8. All right, let's go ahead and take a look. So we know we've got 3 degrees here. So we know we need to have 3 factors. Well, negative 3 is 1, I is 1, and hopefully you recognize that negative I was the other. So I would say, okay, f of x times some constant out front, we'll call that a sub n, times my factors here. If negative 3 is a root, that means x plus 3 is a factor. If I is a root, that means x minus I is a factor. If negative I is a root, x plus I is a factor. All right, let's multiply this out to simplify it. Well, let's go ahead and multiply these together, and just like last time, we're going to have x plus 3 times, this will be x squared minus I squared minus negative 1 squared. Well, negative 1 squared is negative 1. I want to take the opposite of that. It'll be x squared plus 1. All right, at this point now I'm ready to plug this information in here to find out what my a sub n is. So when I evaluate the function at 1, I'm supposed to end up with 8. So we know that f of x is 8. And that's when I plug a 1 in here. So 1 plus 3. Now let's write that again. 1 plus 3 times, well, 1 squared plus 1. Let's see, so that's going to be 4 times 1 plus 1 is 2. So it looks like I get 8, divide both sides by 8, and I get that a sub n is equal to 1. So I don't even have to worry about writing that number out front when I go to my final equation here. So it would look like this. F of x is equal to x plus 3 times x squared plus 1. You can multiply these factors out if you want to. We could go ahead and multiply these out if you wanted to. That answer would be correct, but I think it's simpler just to leave it right in the factored form.